Implementation of Relativity Space's Terran R rocket by Q4 2025, for key phases and $750 million funding allocation for advanced 3D printing techniques. Overview. Relativity Space, an innovative aerospace manufacturer and 3D printing company, is embarking on a groundbreaking project to develop its Terran R rocket with a targeted completion date set for Q4 2025. This ambitious initiative is not just a significant leap for Relativity Space but represents a paradigm shift in the aerospace manufacturing landscape. Central to this project is a planned funding allocation of $750 million specifically directed towards advancing 3D printing techniques which are integral to the rocket's manufacturing process. Key phases of implementation. The development of the Terran R rocket is structured into 4 critical phases, each designed to advance the project from conception to launch readiness. 1. Design and engineering. The first phase emphasizes the design and engineering of the Terran R rocket. This stage involves refining the rocket's design through the use of advanced modeling and simulation tools which facilitate a streamlined manufacturing process. This phase is essential to ensure that the rocket's design meets performance specifications and safety standards while also optimizing for the unique capabilities afforded by 3D printing technology. 2. Prototyping. Following the design phase, Relativity Space will enter the prototyping stage. Here the company will utilize its proprietary 3D printing technology to create prototype components of the Terran R rocket. This approach allows for rapid iteration and testing, drastically reducing the time and costs typically associated with traditional manufacturing methods. The ability to print complex geometries and lightweight structures is expected to significantly enhance the performance of the rocket. 3. Testing. Once prototype components are developed, an extensive testing phase will commence. This phase is critical to validate the rocket's performance under various conditions, ensuring safety and reliability. Testing will involve a series of static fire tests, flight simulations, and other evaluations to gather data on the rocket's operational capabilities. The insights gained during this phase will inform any necessary design adjustments and contribute to the overall safety and effectiveness of the Terran R. 4. Final production. The final phase will focus on scaling up production to meet market demand. This includes refining assembly processes and ensuring that all components are manufactured to the highest standards. As the project nears its completion, final assembly efforts will ramp up, leading to the anticipated first launch of the Terran R rocket by Q4 2025. Funding allocation. The $750 million funding allocation is primarily aimed at enhancing 3D printing capabilities which are expected to revolutionize the manufacturing of rocket components. This investment is anticipated to cover costs across the project phases, ensuring that Relativity Space can maintain its innovative edge. The emphasis on 3D printing technology not only reduces material waste but also allows for the creation of intricate designs that are impossible to achieve through conventional manufacturing processes. Key benefits of 3D printing. 1. Cost efficiency. 3D printing drastically reduces the costs associated with manufacturing complex rocket components, enabling Relativity Space to remain competitive against established aerospace giants. 2. Reduced lead times. The rapid prototyping capabilities afforded by 3D printing significantly shorten lead times, allowing for quicker iterations and faster time to market for new technologies. 3. Material optimization. With advanced 3D printing techniques, Relativity Space can utilize materials more effectively, leading to lighter and stronger components that enhance the rocket's overall performance. 4. Design flexibility. The freedom to design complex geometries opens up new possibilities for rocket design that traditional methods cannot accommodate. Common themes across sources. In reviewing various sources discussing the Terran R rocket, several common themes emerge. 1. 3D printing technology. There is a unanimous consensus on the pivotal role of advanced 3D printing in the manufacturing process of the Terran R rocket. This technology is viewed as a revolutionary approach that not only improves efficiency but also enhances design capabilities. 2. Timeline. The targeted completion date of Q4 2025 is consistently highlighted, indicating a shared understanding of the project's timeline and urgency across reports. 3. Focus on innovation. The Terran R rocket is recognized as a significant advancement in the aerospace industry, with all sources acknowledging its potential to disrupt traditional manufacturing paradigms and enhance operational efficiency. Differences in perspectives. While there is broad agreement on the importance of 3D printing and the project timeline, some sources diverge in their emphasis on the rocket's specific capabilities. Certain discussions focus on technological advancements and the associated cost savings, while others highlight Relativity Space's competitive positioning against established players like SpaceX. Timeline of events. To provide context, here is a timeline of key events leading up to the development of the Terran R rocket. 2021, Relativity Space announces plans for the Terran R rocket, marking a significant step in the company's growth trajectory. 2022, initial funding rounds are completed, laying the groundwork for the project's development. 2023, prototyping begins, showcasing the first applications of advanced 3D printing in creating components for the Terran R rocket. 2024, the testing phase commences, with rigorous evaluations of various components to ensure performance and safety. 2025, final production and assembly efforts ramp up, aiming for the rocket's inaugural launch by Q4. Conclusion. In summary, Relativity Space's Terran R rocket project is poised to redefine manufacturing in the aerospace sector through its focus on advanced 3D printing technology. The structured approach to development, coupled with a substantial funding allocation of $750 million, underscores the company's commitment to innovation and efficiency. As the project progresses toward its target completion date of Q4 2025, it holds the promise of not only enhancing Relativity Space's market position but also transforming the broader aerospace industry landscape. Counterintuitive information in the implementation of Relativity Space's Terran R rocket. 1. 3D printing as a cost-effective solution. While traditional manufacturing methods are often viewed as more reliable and established, the implementation of advanced 3D printing techniques in the Terran R rocket's production challenges this notion. The counterintuitive aspect is that 3D printing, perceived by some as an experimental or niche technology, is actually being positioned as a mainstream solution that can significantly reduce production costs and time. This is particularly surprising given the aerospace industry's historical reliance on conventional manufacturing processes, which are often considered the gold standard for quality and precision. 2. Rapid iteration versus thorough testing. The prototyping phase emphasizes rapid iteration enabled by 3D printing, which may seem at odds with the rigorous testing typically associated with aerospace projects. Conventional wisdom suggests that more time should be spent on thorough testing of prototypes before advancing to the next stage. However, Relativity Space argues that its approach allows for quicker adjustments and refinements based on test results, which could lead to more effective designs in less time. This challenge to the traditional sequence of development phases reflects a broader shift in engineering practices. 3. Complex geometries and simplicity. Another counterintuitive point is the relationship between the complexity of designs achievable through 3D printing and the simplicity of the final product. It might be assumed that more complex geometries would result in more complicated assembly processes. However, Relativity Space asserts that the innovative designs made possible by 3D printing can lead to simpler assembly and reduced component counts. This contradicts the typical expectation that increased complexity in manufacturing leads to higher costs and more difficult assembly. For funding allocation for innovation versus conventional techniques, the substantial $750 million funding allocation toward advanced 3D printing techniques may seem excessive when compared to funding typically directed toward traditional aerospace manufacturing practices. This allocation highlights a counterintuitive belief that investing in innovative technologies can yield greater long-term benefits than simply optimizing existing methods. Rather than relying on established practices, Relativity Space is banking on the transformative potential of 3D printing, which could redefine the future of rocket manufacturing despite the risks associated with venturing into less familiar territory. 5. Market positioning against established players. The Terran R rocket's development is framed as a challenge to established aerospace giants like SpaceX, which could seem overly ambitious given the latter's extensive experience and success in the industry. The counterintuitive angle here is that a relative newcomer is attempting to disrupt a market dominated by established players leveraging cutting-edge technology rather than competing on the same traditional grounds. This approach challenges the perception that only companies with a long history and proven track record can successfully compete in the aerospace sector. 6. Expectation of safety through innovation. The testing phase is typically characterized by an expectation of exhaustive safety protocols and extensive validation processes. However, by adopting innovative manufacturing methods, there may be a perception that the safety and reliability of the Terran R rocket could be compromised. Counterintuitively, Relativity Space is arguing that the integration of advanced 3D printing can enhance safety by enabling the production of more precise and reliable components. This assertion contradicts the assumption that newer technologies inherently come with higher risks. 7. Sustainability claims in rocket manufacturing. The emphasis on reducing material waste through 3D printing may seem contradictory in an industry typically associated with high levels of resource consumption and environmental impact. While the aerospace sector has been criticized for its environmental footprint, Relativity Space's focus on sustainability through efficient manufacturing processes challenges the narrative that aerospace innovation is inherently detrimental to environmental goals. This shift could lead to a re-evaluation of how sustainability is framed in high-tech industries. 8. Timeline expectations. The ambitious timeline for the Terran R rocket's implementation by Q4 2025 may seem unrealistic given the challenges traditionally faced in aerospace development, including regulatory hurdles and technological uncertainties. However, the counterintuitive aspect is that by leveraging 3D printing, Relativity Space is positioning itself to achieve this timeline by streamlining production processes that would typically take much longer. This reflects a belief that innovation can significantly accelerate timelines in a field known for its lengthy development cycles. In summary, the implementation of Relativity Space's Terran R rocket encapsulates several counterintuitive elements that challenge traditional assumptions about aerospace manufacturing safety and market competition. By embracing advanced 3D printing techniques and redefining the norms of the industry, Relativity Space is carving a unique path that may reshape the landscape of rocket production and launch capabilities. The report on the implementation of Relativity Space's Terran R rocket by Q4 2025 highlights several critical aspects that many might overlook despite their significance. These overlooked elements include the unique advantages of 3D printing technology, the implications of the funding allocation, and the competitive landscape of the aerospace industry. 1. Unique advantages of 3D printing technology. While the report emphasizes that advanced 3D printing is central to the Terran R's manufacturing process, the profound implications of this technology often go unexamined. Significance. The ability to use 3D printing in aerospace manufacturing is not merely a means to cut costs or reduce waste, it fundamentally alters how rockets can be designed and built. Traditional manufacturing methods impose restrictions based on the limitations of materials and processes, often requiring complex assembly lines and extensive labor. In contrast, 3D printing allows for the creation of intricate geometries and lightweight structures that would otherwise be impossible or prohibitively expensive to manufacture. This capability can lead to innovations in rocket efficiency, payload capacity, and ultimately mission success. Moreover, 3D printing facilitates rapid prototyping and iteration, enabling companies like Relativity Space to test and refine designs much more quickly than their competitors. This agility can be a game-changer in the fast-evolving aerospace sector, where the ability to respond to new challenges or opportunities can dictate success or failure. 2. Implications of the $750 million funding allocation. The allocation of $750 million towards enhancing 3D printing capabilities is a significant investment, but its implications extend beyond just the immediate development of the Terran R rocket. Significance. Investing heavily in 3D printing technology positions Relativity Space as a potential leader in a future where aerospace manufacturing increasingly relies on additive manufacturing techniques. This funding is not just about producing a single rocket, it is about establishing a new paradigm in aerospace manufacturing. If successful, this approach could lead to lower costs and faster production cycles across the entire industry, forcing competitors to adapt or risk obsolescence. Furthermore, as the technology matures, the potential for spin-off innovations that can benefit other sectors, such as automotive, medical, or even consumer goods, could be substantial. This could create a ripple effect in the economy, fostering new job opportunities and technological advancements. 3. Competitive landscape of the aerospace industry. While the report acknowledges Relativity Space's intent to position itself against established players like SpaceX, it does not delve deeply into the broader competitive dynamics at play. Significance. The aerospace industry is undergoing a transformation, with new entrants challenging traditional powerhouses. The success of Relativity Space in implementing the Terran R rocket could inspire a wave of innovation and investment in the sector. As companies like SpaceX have demonstrated, disruption through technological innovation can lead to rapid market shifts. If Relativity Space successfully leverages its 3D printing capabilities to deliver a reliable and cost-effective rocket, it could attract significant contracts for satellite launches, government missions, and even interplanetary exploration initiatives. This would not only reshape the competitive landscape but also encourage more startups to enter the market, leading to increased innovation and potentially lower costs for consumers. Conclusion. The report on Relativity Space's Terran R rocket project encapsulates a pivotal moment in aerospace history, underpinned by technological advancement and strategic funding. However, the unique advantages of 3D printing technology, the broader implications of the funding allocation, and the competitive dynamics within the aerospace industry are critical aspects that deserve more attention. Recognizing and understanding these factors could provide deeper insight into the future trajectory of space exploration and the commercial space market, making it essential for stakeholders, investors, and policymakers to engage with these themes as the Terran R project progresses toward its 2025 launch. 1. Revolutionizing aerospace manufacturing through 3D printing. The Terran R rocket's development hinges on advanced 3D printing techniques, representing a paradigm shift in aerospace manufacturing. This technology not only reduces costs and production time but also allows for the creation of complex geometries that traditional manufacturing methods cannot achieve. The emphasis on 3D printing is a crucial point for discussion, as it signifies a move towards more efficient, sustainable, and innovative manufacturing processes in the aerospace sector. Analyzing how these advancements can impact other industries could yield valuable insights. 2. Structured phases of implementation. The development timeline of the Terran R is divided into 4 key phases: design and engineering, prototyping, testing, and final production. Each of these phases is critical for ensuring the rocket's success and safety. An in-depth analysis of each phase can reveal the challenges and technological milestones that Relativity Space faces, as well as the strategic decisions made at each step. This structured approach not only facilitates project management but also highlights the importance of iterative development in high-stakes engineering projects. 3. Funding and resource allocation. The $750 million funding allocation for the Terran R rocket is a significant point of interest, particularly in how it is earmarked for specific technological advancements like 3D printing. Understanding the financial strategies behind this funding will provide insight into the prioritization of innovation and efficiency in aerospace manufacturing. Additionally, discussing the implications of such funding on the broader aerospace industry, including competitive positioning against major players like SpaceX, can enhance the understanding of market dynamics. 4. Timeline and strategic positioning. The timeline aiming for the rocket's completion by Q4 2025 is an important aspect of Relativity Space's strategic positioning in the aerospace market. Analyzing the timeline in the context of industry trends, potential market demands, and competitive pressures can provide a comprehensive view of the company's market strategy. This aspect invites discussion on how timely delivery of innovative products can impact a company's reputation and market share, particularly in a rapidly evolving industry. In conclusion, these 4 key points: revolutionizing manufacturing through 3D printing, structured implementation phases, strategic funding allocation, and critical timeline positioning, offer rich avenues for in-depth analysis and discussion, providing a comprehensive understanding of the implications of the Terran R rocket project on the aerospace industry. Here are 3 famous historical cases that are similar in nature to the implementation of advanced technology and funding initiatives similar to the Terran R rocket by Relativity Space. 1. Apollo Program 1961–1972. The Apollo program, conducted by NASA, was a series of space missions aimed at landing humans on the Moon and safely returning them to Earth. The program was initiated following President John F. Kennedy's goal set in 1961 to land a man on the Moon by the end of the decade. The Apollo program involved extensive funding amounting to approximately $25.4 billion, equivalent to over $150 billion today, which was allocated to various phases including design, testing, and production. The first successful crewed landing was Apollo 11 in July 1969, where astronauts Neil Armstrong and Buzz Aldrin set foot on the lunar surface. The use of advanced technologies including the Saturn V rocket and lunar module showcased innovation in aerospace engineering similar to the 3D printing techniques being developed for the Terran R rocket. 2. Space Shuttle Program 1972–2011. NASA's Space Shuttle program was another landmark in space transportation, allowing for reusable spacecraft to carry astronauts and cargo to and from low Earth orbit. Initiated in the 1970s, the program was driven by the need for a reliable and cost-effective means to access space. The shuttle underwent multiple phases from design to testing and operation, with substantial funding from the federal government amounting to roughly $196 billion over its lifetime. The program saw numerous advancements in technology, including improvements in materials and safety systems. The shuttle's operational capabilities allowed for significant scientific research and international collaboration akin to the goals of modern aerospace firms like Relativity Space, focusing on innovation and efficiency. 3. International Space Station 1998–present. The International Space Station ISS is a multinational collaborative project that includes contributions from NASA, Roscosmos, ESA, JAXA, and CSA. First launched in 1998, the ISS has served as a microgravity and space environment research laboratory where scientific research is conducted in astrobiology, astronomy, meteorology, and physics. The project required extensive funding and resource allocation, with costs exceeding $150 billion, making it one of the most significant engineering projects in history. The ISS exemplifies international collaboration in space exploration and the use of cutting-edge technology, including advances in life support systems and materials science similar to the innovations being pursued in the development of the Terran R rocket by Relativity Space. These historical cases illustrate the challenges and triumphs of implementing advanced technologies and securing funding for ambitious aerospace projects, reflecting the themes present in Relativity Space's plans for the Terran R rocket. Future outlook: predictions for the implementation of Relativity Space's Terran R rocket by Q4 2025. As Relativity Space approaches the completion of its Terran R rocket by Q4 2025, numerous factors will shape the future landscape of aerospace manufacturing and space exploration. Here are key predictions regarding the trajectory of this initiative. Its impact on the industry and the broader implications for space travel. 1. Advancements in 3D printing technology. The primary focus of the Terran R initiative is the incorporation of advanced 3D printing techniques. As Relativity Space allocates $750 million towards enhancing these capabilities, we anticipate significant breakthroughs in materials science and manufacturing processes. By 2025, we expect increased efficiency. 3D printing will streamline production, reducing lead times and costs for rocket components. This efficiency will not only benefit Relativity Space but will also influence competitors, prompting them to adopt similar technologies or enhance their existing manufacturing processes. Complex designs. The ability to create more intricate geometries through 3D printing will lead to innovative rocket designs that optimize performance and reduce weight. This could result in rockets that are more efficient and capable of carrying larger payloads or achieving greater distances. Sustainability. Enhanced 3D printing techniques will minimize material waste and allow for the use of sustainable materials, aligning with broader industry trends towards environmental responsibility. 2. Competitive positioning in the aerospace industry. As the Terran R rocket nears its completion, its performance and capabilities will position Relativity Space competitively against established players like SpaceX and Blue Origin. Predictions include market disruption. The Terran R's cost-effective manufacturing will challenge traditional pricing models within the aerospace sector, potentially leading to lower launch costs across the board. This could democratize access to space for smaller companies and nations looking to deploy satellites or conduct research. Diverse applications. The versatility of the Terran R could attract a wide range of customers beyond governmental contracts, including commercial entities looking for reliable launch services for satellite space tourism and interplanetary missions. Strategic collaborations. As Relativity Space gains traction, expect partnerships with other aerospace companies, tech firms, and governmental bodies, enhancing their technological capabilities and market reach. 3. Impact on space exploration initiatives. The successful deployment of the Terran R rocket will have a broader impact on space exploration initiatives, particularly with regard to upcoming missions aimed at the Moon, Mars, and beyond. Supporting NASA's Artemis program. With the increasing demand for launch vehicles for lunar missions, the Terran R could serve as a vital asset for NASA's Artemis program, which aims to return humans to the Moon by the mid-2020s. Relativity Space could secure contracts for cargo delivery to support lunar infrastructure. Mars missions. As interest in Mars exploration grows, the Terran R's capabilities may facilitate missions aimed at the Red Planet, including scientific research and potentially crewed missions. This could position Relativity Space as a key player in interplanetary logistics. International space collaboration. The rocket's launch capacity may encourage international collaborations on space exploration, enabling countries with limited access to develop partnerships with Relativity Space for satellite launches and exploratory missions. 4. Long-term aerospace trends. The development and potential success of the Terran R rocket will echo through the aerospace industry, influencing long-term trends. Shift towards reusability. The focus on cost and efficiency will further drive the industry's shift towards reusable rocket technology. While Relativity Space has adopted innovative manufacturing techniques, we predict that advancements in reusability will also be a focal point for competitors, leading to a new standard in the industry. Emerging markets. The success of the Terran R could encourage new entrants into the aerospace market, especially from countries and startups eager to participate in the burgeoning space economy. This democratization of space access will spur innovation and competition. Enhanced regulatory frameworks. As more players enter the space launch sector, regulatory frameworks will evolve to ensure safety and sustainability, impacting how companies like Relativity Space navigate their operations. Conclusion. The implementation of Relativity Space's Terran R rocket by Q4 2025 marks a pivotal moment in the aerospace industry. With a focus on advanced 3D printing and a competitive edge against established giants, the project is poised to not only revolutionize manufacturing but also reshape the landscape of space exploration. As the industry moves towards more efficient, cost-effective, and sustainable practices, the Terran R will likely play a significant role in defining the future of space travel and exploration.